Hello students, I am Dr. Premlata Verma from Government Bilasa Girls PG College, Bilaspur, and I am going to deliver a lecture for MSc Mathematics Paper 3 Topology. The topic of today's lecture is some theorems on connectedness. Students, this topic of connectedness are taught in some universities in MSc semester 1 syllabus and in some universities in MSc semester 2 syllabus. So, what we are going to prove in our today's lecture is theorem 1. The statement is as follows. If every 2 points of a subset E of a topological space X are contained in some connected subset of E, then E is a connected subset of X. Theorem 2 statement is as follows. A topological space X tau is connected if and only if every non-empty proper subset of X has a non-empty frontier. So, in order to prove these two theorems, we shall have some preliminaries. First, let us define disconnected space. A topological space X tau is said to be a disconnected space if and only if X can be expressed as a union of two non-empty tau separated sets, that is, if and only if there exists two subsets C and D of X such that X is equal to C union D, C is non-empty, D is non-empty, and C closure intersection D is equal to phi and C intersection D closure is equal to phi. Tau separated sets means C closure intersection D is equal to phi and C intersection D closure is equal to phi. So this is the definition of disconnected space, and points 2 and points 3 are theorems for disconnected space, and once we have proved theorem 2 and theorem 3, we consider all the 3 points as definition of disconnected space. So what is the second definition of disconnected space? A topological space X tau is said to be a disconnected space if and only if there exists a non-empty proper subset of X which is both tau open and tau closed. And third, a topological space X tau is said to be a disconnected space if and only if X is the union of two non-empty disjoint tau open sets, or X is the union of two non-empty disjoint tau closed sets. In our main theorems, for proving theorem 1, we shall be using this definition 1, and in order to prove theorem 2, we shall be using this definition 2. Now, the theorem which is required to prove our main theorem 1 is, let X tau be a topological space and let E be a connected subset of X such that E is contained in A union B where A and B are separated sets. Then E is contained in A or E is contained in B, that is E cannot intersect both A and B. Students, we must remember that here E is a connected subset of X. A and B are tau separated sets. That means A closure intersection B is equal to phi and A intersection B closure is equal to phi. And this connected subset E of X is contained in A union B. Then E is either contained in A or it is contained in B. Now, let us come to prove our main theorem, theorem 1. The theorem states, if every 2 points of a subset E of a topological space X are contained in some connected subset of E, then E is a connected subset of X. First, let us uh, understand what this theorem states. X is a topological space and E is a subset of X. In our theorem, we have to prove that E, if E is a subset of X and if every 2 points of E are contained in some connected subset of E, then E itself is connected. That means if A and B are any pair of points of E, then if A and B both are contained in some connected subset F1 of E. Similarly, for other pair AC, there exists a connected subset F2 of E. Similarly, for C and D points of E, there exists another connected subset F3 of E. Then E itself will be connected. So, let us start the proof of our theorem. Let X tau be a topological space and E be a subset of X such that every 2 points of E are contained in some connected subset of E. What we have to prove? That E is connected. In order to prove this theorem, we will use the method of contradiction. For suppose that E is not connected. That means E is disconnected. Then we have learned the definition of a disconnected space, that E is disconnected. Therefore, there exists two non-empty subsets A and B of X such that E is equal to A union B and A closure intersection B is equal to phi and A intersection B closure is equal to phi. A and B are non-empty sets. Now, since A and B are non-empty, therefore there exists at least one element in A and there exists at least one element of B. So, suppose that A is any element in A and B is any element in B. Now, because A is an element of A, therefore A also belongs to E. B is an element of B, therefore B also belongs to E. So, thus, A and B are elements of E.